Welcome back to the Deep Dive. Today, our mission is, well, it's to tackle a pretty dense source, a new paper from Microsoft Research. We want to pull out the key things you need to know about what looks like the next big step in AI reasoning.
Yeah, it feels like we're really shifting gears, moving beyond seeing LLMs as these, solitary thinkers.
Exactly. The paper calls it the era of agentic organization. So less lone genius, more teamwork.
Precisely. They introduced this new framework called asynchronous thinking, or async think for short. It's a fundamentally different way for these models to structure how they, think.
Okay, so help us picture this.
Right.
Currently, we mostly have, what, sequential.
Right. Sequential is the classic approach. Step 1, step 2, step 3, like one person working through a problem start to finish.
And then there's parallel thinking.
Yep. That's more like launching several independent attempts at the same time. You generate maybe 4 different solutions or lines of reasoning and then just pick the best one at the end.
Like hedging your bets.
Kind of. But async think is presented as this third, more sophisticated way. It's about teaching the LLM to be more like an efficient project manager.
A project manager, overseeing a team.
Exactly. A team of internal workers. It learns to organize its thinking into these dynamic structures that can run concurrently, side by side.
So what was the problem they were trying to solve? Why move beyond parallel thinking if that already exists?
Efficiency, mainly, and flexibility. Current parallel methods often get bottlenecked by the slowest attempt finishing. Plus, they usually rely on these fixed, predefined workflows. Someone has to manually decide how to parallelize up front.
Ah, okay. So async think is more adaptive.
That's the key. It learns the best way to organize itself on the fly. And the results they report are pretty striking as something like 28% lower inference latency compared to those standard parallel approaches.
28% faster, while also getting better answers on tough tasks like math reasoning.
Yeah, that's the claim. Better and faster because the organization itself is smarter. Its efficiency baked right into the reasoning process.
All right, I'm intrigued. Let's get into the nuts and bolts. How did they actually build this internal manager structure? You mentioned an organizer-worker thing.
Right, the organizer-worker protocol. They use a helpful analogy from computer systems, which I think makes it pretty clear.
Okay, lay it on us.
So think of the whole LLM system. An agent within that system is like a single CPU core. It does the work.
Got it. One worker bee.
Then you have the agent pool. This has a fixed capacity, let's call it C dollars. That's like your multi-core CPU. It defines how many agents, how many cores you can have running tasks at the very maximum.
Okay, so limit on the parallel processing power.
Exactly. And crucially, the organization policy. That's like the program, the software, deciding how to use those cores. It's generated dynamically, figuring out the best strategy, what to run in parallel, when to wait for results, when to bring things back together.
And the really clever part is, the LLM plays both roles.
Yes. The same underlying model architecture, the same brain, if you will, acts as both the organizer, the manager, handling the overall strategy and coordination, and the workers executing the specific subtasks.
So it's managing itself. How does the organizer actually, tell the workers what to do? Is it complex code?
No, and that's another elegant part. It's all done through simple text commands generated right within the LLM's output. There are basically 4 key actions, the vocabulary of async think.
Okay, what if?
First, the most basic one is think. This just means the organizer continues its own reasoning process, its own chain of thought, like, I need to figure out the next step myself.
Simple enough. What about the parallel stuff?
That's where fork comes in. The organizer generates a special tag, like FORKI, calculate the specific value FORKI. This assigns that subquery, that job, to an available worker agent identified by the index I.
Okay, so it delegates a piece of the problem.
Precisely. Then, naturally, you need join. The organizer generates JOINI. This is the signal that it needs the result back from worker I. And here's a key point. The organizer might actually pause its own thinking here, waiting for that worker to finish.
Ah, so it synchronizes. It waits for the report back.
Exactly. And when the worker result comes back, it gets inserted right into the organizer's context, like JOINI. The calculated value is 5 JOINI. Then the organizer can use that information.
Makes sense. Fork to delegate, join to collect, and the last action.
Answer. That's simply the organizer deciding, okay, I have everything I need, and outputting the final result, terminating the whole process.
What strikes me is how fluid this sounds. It's not a rigid flowchart.
That's absolutely central. The whole
Yeah.
structure, which tasks to fork, when, how many, when to join them, it's all generated auto-regressively. The model decides step by step as it thinks.
So it's learning the management strategy itself just through generating these text tags.
Exactly. It's all happening right at the input-output level of the LLM.
But wait a minute. If you're constantly forking and joining, doesn't that create its own overhead, context switching, managing these workers? Does that actually end up being faster? It sounds like it could just slow things down.
That is the million-dollar question, right? And it gets to the heart of why the training is so critical. It's not just about enabling parallelism. It's about learning when it's actually beneficial.
Okay.
The efficiency doesn't come from just throwing more workers at the problem. It comes from the organizer learning to be smart about it. It learns to only fork tasks that are sufficiently independent and time-consuming, where the parallel speed-up outweighs the coordination cost.
So it learns not to micromanage pointless tiny tasks.
Precisely.
Yeah.
It avoids unnecessary forks. In
Hmm.
fact, regular sequential thinking is just a special case of async think, where the learned policy decides, you know what, for this problem, zero force is the best strategy.
Okay, that makes more sense. The efficiency is in the learned policy, which brings us nicely to the training process. How do you teach an LLM to be a good project manager? That sounds hard.
It definitely is. It's not just about mimicking examples. It's about developing strategic judgment. They used a two-stage approach. Stage one is what they call cold start format fine-tuning, or SFT. Basically teaching the model the rules of the game.
The grammar, you mean? Like how to use F4K and join correctly.
Exactly that. The syntax, the format. They use synthetic examples actually generated by GPT-4o initially to show the model what these fork join sequences look like.
Did that work straight away?
Well, they hit a bit of a snag. The initial examples generated by GPT-4o tended to be overly simple. They mostly showed either a very basic interleaved pattern, fork 1, join 1, fork 2, join 2, or a fork all, join all pattern.
So not really exploring the potential for more complex overlapping concurrency.
Right. The model was defaulting to easy, almost sequential-like structures, so the researchers had to step in during this SFT stage. They essentially injected randomness. They created synthetic training examples with much more diverse, truly concurrent thinking structures, different timings for forks and joins, overlapping tasks. This forced the model to see the possibilities before it started learning the strategy.
Okay, so SFT teaches the how, then comes stage 2.
Stage 2 is reinforcement learning, RL. This is where the model learns the why and when. It learns the actual strategic organization policy, aiming for answers that are both correct and efficient.
And RL means rewards, right? How did they incentivize both accuracy and this organizational skill?
Through a clever reward system with 3 main parts. It's all about balancing different goals.
Okay, part 1, probably accuracy.
Yep, accuracy reward. Simple enough. You get rewarded if the final answer is correct. For problems with multiple solutions, it's proportional to how many correct ones you find.
Standard stuff, part 2.
Format reward. This is about discipline. It gives an immediate negative reward, a penalty, if the organizer messes up the rules.
Like what kind of mess-ups?
Things like trying to fork more workers than the pool capacity $1 allows, that's an overflow error. Or using the same fork index twice. Or, critically, just stopping without ever generating a final answer tag. It teaches the organizer to follow the protocol.
Keep the manager in line. Okay,
Yeah.
and part 3, you mentioned this earlier, the concurrency reward.
Yes, the thinking concurrency reward, they call it dreaded dollar. This is really unique and directly targets efficiency.
How does it work?
It basically rewards the organizer for keeping his workers busy productively. At each step, it looks at how many workers are currently active compared to the total pool capacity. The higher the ratio at SIA time, the bigger the reward.
So it's explicitly encouraged to maximize parallelism, to use its team effectively.
Exactly. It directly fights against the tendency to just default back to single-threaded, sequential thinking. It incentivizes finding those opportunities for concurrent work.
Okay, so the RL shapes the strategy using these 3 rewards. Now, you mentioned latency reduction earlier. How do they measure the real speed gain from this complex organization? Wall clock time depends on the hardware, right?
Precisely. You can't just time it with a stopwatch. They use a metric called critical path latency.
Critical path latency, what does that represent?
Think of it as the theoretical minimum time the whole process must take, even with infinite parallel processors. It measures the length of the longest chain of dependent steps.
So tasks that have to happen one after the other.
Exactly. If task B depends on the result of task A, that adds to the critical path. But if task C can run completely independently while A and B are happening, it doesn't necessarily extend that critical path. Async think aims to shorten this essential sequential backbone by doing more work off to the side concurrently.
Okay, I think I get it. It's like managing a construction project. Some things have to happen in order for a foundation before walls. But you can have the electricians and plumbers working in different rooms at the same time. Async Think tries to maximize that simultaneous work to shorten the overall project time, the critical path.
That's a great analogy. It abstracts away the specific hardware speed and measures the inherent efficiency of the logical plan itself.
And did this metric show Async Think winning?
Yes, significantly, especially on those complex math reasoning benchmarks. We talked about AIM and AMC problems. These are notoriously difficult.
What were the numbers like?
Well, for instance, on AIM 24, Async Think didn't just get the best accuracy, 38.7%, but its critical path latency was way down at 1468.0.
And compared to the baseline?
The best standard parallel thinking model they compared against had a latency of 2048.0, so Async Think was considerably faster in terms of its core logic.
Wow, and that latency difference holds even when you factor in the complexity.
Yes, and what's interesting is that Async Think achieved this lower latency even when its individual worker responses were limited, like 512 tokens, whereas the parallel baselines often used much longer response limits, like 2,000 tokens.
So it's not just about thinking longer, it's about thinking smarter, more organized. Shorter, targeted thoughts in parallel beat longer brute force attempts.
Exactly. It confirms that the overhead of the fork join management is more than paid back by the efficiency gains when the policy is learned well. Organized thinking wins.
It's one thing to see the numbers, but can we visualize this? The paper had some examples, right? Like that geometry problem.
Oh yeah, the tetrahedron example.
Yeah.
Finding the cosine of an angle CMDT. That really shows the strategy in action.
What did the async think organizer do?
Okay, so it had, let's say, 4 agents available in its pool. Instead of just starting down one path, it immediately forked out tasks to 3 different workers simultaneously.
3 different approaches.
Yes, that's the smart part. It assigned worker 1 to use the standard Cartesian coordinate method, often reliable but can be calculation heavy.
Right.
Worker 2 got assigned an alternative coordinate system, maybe looking for a simpler geometric insight. And worker 3 was told to assume the tetrahedron had unit edge lengths, a common trick to simplify calculations if the result is scale invariant.
So it hedged its bets methodologically, covering different bases at once.
Precisely. Then the organizer waited using join actions. It collected the results from all 3 workers. And since all 3 independent methods came back with the same answer, the organizer had really strong built-in verification.
Consensus building through parallel exploration.
Yeah.
That's clever. High confidence before giving the final answer.
It's dynamic, multi-perspective reasoning happening concurrently.
We also saw this adaptive approach in that countdown numbers game example, right? Finding 4 ways to make 8088 using arithmetic.
Yes, the multi-solution countdown task. That showed a different facet of management strategy.
How so?
The organizer started maybe forked worker 1 to look for solutions involving multiplication. But crucially, while worker 1 was busy thinking, the organizer didn't just sit idle, it continued its own thinking process. Think action. Maybe analyzing the problem structure further.
Okay, planning ahead.
Then it joined worker 1's result. Let's say worker 1 only found 2 of the required 4 solutions.
Right. Task incomplete.
So the organizer didn't just give up or restart blindly. It analyzed the partial results, saw what was missing, and adapted. It then forked a new, much more focused task. Maybe something like, okay, worker 2, now specifically look for combinations starting with the number 89.
Targeted delegation based on intermediate results. That's the divide and merge idea.
Exactly. It's receiving feedback, adjusting the plan, and issuing new specific instructions to efficiently fill the gaps. It's not a fixed, predetermined parallel plan. It's reactive and strategic management.
This is really impressive. But the ultimate test is always generalization, isn't it? Did it just learn to manage math problems, or did it learn a truly general skill?
That's what their zero-shot experiment aimed to find out. And the results were, frankly, quite surprising.
What did they do?
So remember, the async think model we've been discussing was trained only on that multi-solution countdown arithmetic task. Numbers, basically.
Okay, purely numerical training.
Then they took that exact same trained model and just threw it at a completely different type of problem. A $4 times 44 Sudoku puzzle task. No further training, no examples of Sudoku.
Wow. Okay, arithmetic to Sudoku, that's Quite a leap. How did it do?
Remarkably well. Async Think got 89.4% accuracy on the Sudoku puzzles, significantly outperforming both standard parallel thinking, 84.2%, and sequential thinking, only 65.7%.
And in a latency.
Lower again. Async Think's critical path latency was 208 3.0, whereas the parallel baseline was much higher at 3694.7, so faster and more accurate on a task it had never seen before.
That really does suggest that it learned something deeper than just arithmetic tricks.
It implies it learned a generalized organization policy. The abstract skill of analyzing a problem, decomposing it into potentially independent parts, using fork to manage concurrent exploration, and using join to synthesize results.
A transferable managerial skill set for thinking.
Exactly. They even showed anecdotal evidence of this policy working on things like graph theory problems, finding vertex covers, and even complex biological reasoning about genetics. The core skill transfers.
So wrapping this up, what's the big takeaway for someone listening, maybe a developer, maybe just someone interested in where AI is going?
I think the core message is that the next big performance jump in AI might not just come from making the models bigger or feeding them more data, though that will continue.
Yeah.
It's also about teaching them how to think more effectively.
Moving from raw intelligence to organized intelligence.
Yeah. We're teaching them to be efficient, adaptive project managers of their own thoughts, trading that lone genius model for a well-run, collaborative internal team.
And where does this lead next? The paper must have hinted at future directions.
Oh, definitely. One obvious path is recursive agentic organization. Imagine a worker agent, when faced with a complex subtask, dynamically becoming an organizer itself, forking out sub-subtasks to its own team.
Whoa, like nested teams. Hierarchies of thinking.
Exactly, for really complex, deeply nested problems. But perhaps the most thought-provoking idea they touch on is human-AI agentic organization.
How would that work?
Well, two ways. You could imagine you being the organizer. You have a complex research project, and you use fork commands to delegate different analysis tasks to a pool of specialized AI workers running concurrently. You manage the AI team.
Okay, AI assistants on steroids.
But maybe more interestingly, the other way around. An AI organizer is working on a problem, identifies a step that requires, say, subjective judgment or ethical consideration.
Something humans are still better at.
Right. And the AI generates a fork targeted at a human. F-O-R-K human. Does this conclusion seem fair and unbiased? F-O-R-K human. The AI delegates to a human as worker for specific input.
That really changes the dynamic, doesn't it? If AI can learn not just to think, but to organize thinking this effectively, even incorporating human input seamlessly into its workflow, how does that reshape how we collaborate with AI down the line?
That's the big question they leave us with. It's not just about faster answers. It's about fundamentally new ways of structuring complex cognitive work, potentially blending human and machine capabilities in truly novel organizational structures.
A lot to think about there, from lone genius to organized teams, and maybe soon to human-AI hybrid organizations. Fascinating stuff.